What if I told you that somewhere out there in the vast ocean of stars, one of them is doing the impossible rewinding time? Picture a celestial body that glows brighter, grows hotter, and appears to shed its wrinkles like some cosmic Benjamin Button. This isn't a plot twist from a sci-fi novel. It's a real, documented mystery that has left astronomers scratching their heads. Stars, like all living things, or so we thought, are supposed to follow a predictable path, born from clouds of gas, burning brightly for billions of years, then fading into old age. But this star, it's flipping the script, and the most astonishing part, we caught it in the act, thanks to a telescope so advanced it feels like peering into the universe's diary. Now let's pause for a second and think about what this means. For centuries, we've mapped the lives of stars with confidence, tracing their arcs from ignition to quiet demise. But this discovery, this star that ages backward, throws a wrench into everything. It's like watching a river flow uphill or a candle relight itself. How can something so fundamental, so seemingly set in stone, just reverse? The implications are staggering. Could there be others like it? Are we missing a whole chapter in the story of stellar evolution? And what does it say about the universe's hidden rulebook? That's exactly what we're diving into today. This isn't just a tale of cosmic oddities. It's a detective story, a technological triumph, and a humbling reminder of how much we still don't know. The telescope that spotted this anomaly isn't just a piece of machinery. It's a time machine in its own right, revealing secrets written in starlight. So buckle up. By the end of this journey, you'll see the night sky a little differently, knowing that even the most familiar twinkles might be hiding mind-bending surprises. Ready to unravel the mystery of the star that forgot how to grow old? Let's begin. To understand just how bizarre this star's behavior is, we need to rewind to what we thought we knew about stellar evolution. Imagine a star's life as a candle burning steadily. You light it, it shines bright, and over time it dims until the flame flickers out. That's the universal script stars are supposed to follow. But this one, it's as if someone poured fresh wax onto the candle, making it burn even brighter as time passes. Scientists first flagged this cosmic rebel because it refused to play by the rules. Its brightness didn't just fluctuate randomly, it followed a pattern that suggested it was growing younger. And then there's the chemistry. Stars, like people, accumulate certain wrinkles as they age. Elements like helium and heavier metals build up in their cores as they burn through fuel. But this star's outer layers showed fewer of these aging markers, almost as if it had hit a cosmic reset button. So what could possibly cause this? One leading theory involves a phenomenon called stellar mergers, when two stars collide and essentially rejuvenate the resulting object. Think of it like mixing two half-empty glasses of water. Suddenly, you've got a fuller glass and the system appears younger, another wild possibility. The star might be stealing material from a nearby companion, fueling itself with fresh hydrogen to delay its inevitable decline. But here's the twist: neither theory fully explains all the oddities observed. That's the real thrill of this mystery. It's not just challenging what we know, it's exposing gaps in our knowledge we didn't even realize existed. And that's what makes this discovery so revolutionary. It's not just about one oddball star. It's a wake-up call that the universe might have shortcuts, loopholes, or even entirely new physics we've yet to uncover. Every time we think we've mapped the rules of cosmic life and death, the cosmos throws us a curveball. This star isn't just aging backward, it's rewriting the playbook. This cosmic detective, the telescope that spotted the star defying time, isn't your average backyard stargazing tool. It's a technological marvel, a precision instrument designed to catch whispers of light from the farthest corners of the universe. Imagine trying to spot a single candle flickering on the moon from Earth. That's the level of sensitivity we're talking about. What sets this telescope apart is its ability to not just see distant objects, but to read them like a book, analyzing the faintest glimmers of starlight for clues about composition, temperature, and even motion. At its core, this telescope relies on next-generation optics mirrors so finely polished and aligned that they can collect and focus light with almost no distortion. But the real magic happens in its detectors. These aren't ordinary cameras. They're ultra-sensitive sensors capable of picking up wavelengths invisible to human eyes, from infrared to ultraviolet. When combined with powerful spectrographs devices that split light into its component colors like a cosmic prism, they reveal the chemical fingerprints of stars. That's how astronomers noticed something off about our time-bending star. Its spectral lines, the telltale signatures of elements like hydrogen and helium, didn't match the expected patterns for its supposed age. What's even more groundbreaking is the telescope's ability to monitor changes over time. Unlike earlier instruments that provided snapshots, this one operates like a surveillance camera, continuously tracking subtle shifts in brightness and spectrum. That's how it caught the star's reverse aging in action, a gradual brightening and chemical youthing that would have been missed by telescopes just a decade ago. And let's not forget its location. Perched high above Earth's blurring atmosphere or nestled in the pristine darkness of remote observatories, where the skies are so clear the stars don't twinkle, they speak. This discovery isn't just a win for astronomers, it's a testament to human ingenuity. Every time we build a telescope that pushes the limits of what's possible, we're essentially inventing a new way to see. From Galileo's first crude spyglass to this cutting-edge marvel, each leap in technology peels back another layer of the universe's mysteries. And who knows what else is out there waiting for the right tool and the right curious minds to uncover it. Stars aren't supposed to be unpredictable. Their life cycles are cosmic clockwork, written in the language of physics and chemistry, playing out over millions or even billions of years. Picture a newborn star, a swirling cradle of gas and dust collapsing under its own gravity until the pressure at its core becomes so intense that atoms of hydrogen slam together, igniting the furnace of nuclear fusion. That moment when a star flickers to life sets it on an irreversible path. For stars like our Sun, that means a steady burn for billions of years, fusing hydrogen into helium, shining with reliable warmth. But for massive stars, it's a different story. They live fast and die young, burning through their fuel in a cosmic sprint before exploding in spectacular supernova. What makes this backwards aging star so baffling is how it defies these fundamental rules. Think of it like a tree. You can count its rings to know its age, and the chemistry of its layers tells the story of droughts, storms, and seasons. Stars have their own version of rings, the elements in their atmospheres. As they age, fusion creates heavier elements like carbon and oxygen, leaving behind a chemical fingerprint of time. But this star, its outer layers show less of these aging markers than they should, as if it's somehow scrubbing away the evidence of its own history. So where does this leave us? Either we're missing a critical piece of stellar physics, or we've stumbled onto something entirely new. One possibility is that the star isn't alone. It might be part of a binary system, siphoning fresh hydrogen from a companion like a cosmic fountain of youth. Another theory suggests a violent past, a collision between two stars that scrambled their life cycles, leaving behind what looks like a younger, reinvigorated object. But here's the catch: none of these explanations perfectly fit all the data. That's the beauty of this mystery. It's not just about solving a puzzle. It's about realizing the puzzle might have pieces we didn't even know existed. The implications ripple far beyond this one star. If stellar aging isn't as one-directional as we thought, what else have we gotten wrong? Could there be entire populations of stars hiding in plain sight, masquerading as younger or older than they really are? And if the rules aren't as rigid as we believed, what other cosmic surprises are waiting to be uncovered? This isn't just a challenge for astronomers, it's an invitation to rethink the very foundations of how we understand the universe. After all, the cosmos has never been one to stick to the script. When faced with a star that seems to laugh in the face of cosmic rules, scientists don't just throw up their hands, they get creative. The leading explanation for this celestial Benjamin Button involves a dramatic stellar merger. Picture two aging stars locked in a slow dance for eons until gravity pulls them into a violent embrace. The collision wouldn't just mix their material, it could reset the clock. Fresh hydrogen from the smaller star floods the core of the larger one, like pouring high-octane fuel into an engine. The result, a star that appears younger, burning brighter with renewed vigor. But here's the catch: mergers are messy. They leave behind telltale signs, unusual rotation speeds, chemical imbalances, and while this star shows some of those clues, they don't quite add up perfectly. Then there's the gravitational sleight of hand theory. Imagine the star isn't alone, it's part of a hidden duo, orbiting a companion we can't yet see. As they swing around each other, tidal forces might stretch and compress the star's outer layers, stirring up fresh fuel from deep within and masking its true age. It's like shaking a snow globe. The settled debris, the star's age markers, get tossed back into the mix, creating the illusion of youth. But even this elegant idea hits a snag. Detailed observations haven't found clear evidence of a gravitational partner, leaving astronomers to wonder if the culprit is something even stranger. That's where the wild cards come in. Some researchers whisper about exotic matter particles or forces we haven't discovered yet altering the star's internal physics. Others toy with the idea of cosmic rejuvenation zones, regions of space where unknown processes might temporarily reverse aging. And let's not forget the humbling possibility: maybe our understanding of stellar evolution has blind spots. After all, stars are laboratories of extreme physics, and nature often outwits our textbooks. What makes these theories so thrilling isn't just their creativity, it's their stakes. If mergers can fake youth, how many other stars have we misjudged? If hidden companions or exotic physics are at play, what else might they explain? Every unexplained flicker of light is a reminder the universe still holds cards close to its chest. And that's the real gift of this backwards aging enigma. It's not just challenging answers, it's revealing how much more vibrant, more unpredictable, and more alive the cosmos might be than we ever dreamed. Now let's venture into the shadows of the cosmos, where an invisible player might be pulling the strings: dark matter. This mysterious substance, which outweighs all the visible matter in the universe 5-to-1, has long eluded direct detection. We know it's there because of its gravitational grip on galaxies, bending light and sculpting the cosmic web. But what if its influence isn't just gravitational? What if dark matter is meddling with the very life cycles of stars? One provocative idea suggests that dark matter particles, drifting through a star like ghosts, could alter its internal dynamics. Picture this: as these invisible particles collide with ordinary matter in the star's core, they might carry away heat, subtly cooling it. Counterintuitively, this cooling could delay the star's aging by slowing nuclear fusion, like turning down the flame under a boiling pot. But here's the twist: under certain conditions, dark matter might do the opposite. If enough of it accumulates in the core, its annihilations could inject fresh energy, rejuvenating the star like a cosmic defibrillator. Suddenly, a star that should be fading might flare back to life, mimicking the illusion of reverse aging. Then there's the dark matter capture theory. Stars in dense regions of dark matter, like near the center of galaxies, could act as nets trapping these particles over time. As the dark matter builds up, its interactions might stir the star's fuel, mixing fresh hydrogen into the core and erasing the chemical fingerprints of age. It's like shuffling a deck of cards mid-game. The star's outer layers no longer reflect its true history, but here's the catch: dark matter's role is still a speculative leap. No one's yet observed it directly, let alone caught it red-handed tampering with stars. Yet the tantalizing possibility remains. If dark matter is behind this stellar time reversal, it would solve two cosmic mysteries at once, explaining both the star's bizarre behavior and revealing dark matter's hidden hand in shaping the universe. Until then, this idea dangles at the edge of our understanding, a reminder that the universe's greatest secrets often lurk just beyond the light. The universe has never been shy about showing off its quirks, and this backwards aging star is just the latest in a long line of celestial rule breakers. Take hypervelocity stars, for example, cosmic speedsters hurtling through galaxies so fast they're essentially evicted from their neighborhoods. These stars don't just drift, they're flung outward by gravitational slingshots, often from close encounters with supermassive black holes. Then there's the zombie stars, white dwarfs that should have faded into oblivion, but instead get a second lease on life by siphoning material from a companion until they reignite in explosive thermonuclear bursts. These aren't just oddballs, they're proof that the universe loves a good plot twist. So where does our time-defying star fit in? Unlike hypervelocity stars, which break the rules of motion, or zombie stars, which cheat death, this one messes with the very fabric of time. It's not just behaving unusually, it's rewriting the timeline of its own existence. That's what sets it apart. Past discoveries challenged where stars could go or how they could die. This one challenges when they're supposed to age. It's as if we've spent centuries studying a clock's ticking hands, only to stumble upon one that ticks backward. Yet these historical oddities share a common thread. Each one forced astronomers to rethink their assumptions. When the first hypervelocity star was spotted, it upended ideas about galactic gravity. Zombie stars revealed that stellar death isn't always final. Now, this reverse aging enigma is pushing us to question whether stellar evolution is as one-directional as we thought. The real lesson here isn't just about individual stars. It's about the universe's flair for subverting expectations. Every time we think we've mapped the boundaries of possibility, the cosmos throws another curveball, reminding us that the textbook is still being written. What's truly exciting is how these discoveries build on each other. Hypervelocity stars taught us about extreme gravity. Zombie stars unveiled the chaos of stellar resurrection. Now, this backwards aging marvel might be hinting at entirely new physics or hidden chapters in the lives of stars we thought we understood. The more outliers we find, the clearer it becomes. The universe isn't just vast, it's endlessly inventive. And that's the real takeaway. Whether it's a star racing across the galaxy or one that's forgotten how to grow old, each one is a clue, a piece of a puzzle we're only beginning to assemble. So the next time you look up at the night sky, remember, the ordinary stars might be the exception, not the rule. Decoding the secrets of this cosmic anomaly begins with starlight, not just its glow, but the hidden messages trapped within every wavelength. When astronomers train their telescopes on this backwards aging star, they're not just capturing an image, they're dissecting its very essence through spectroscopy. Imagine shining sunlight through a prism and seeing it split into a rainbow. Now, replace that prism with a high-tech spectrograph, and the rainbow becomes a barcode, each line, gap, and smudge revealing the star's chemical makeup, temperature, and even its motion through space. The data tells a story that defies expectations. Hydrogen lines appear stronger than they should for a star of its supposed age, like finding fresh paint on an antique vase. Helium, typically more abundant in older stars, shows up in strangely low amounts. And then there's the star's metallicity, the concentration of heavier elements forged over time, which reads more like a youthful star's resume than that of a seasoned elder. These aren't just minor discrepancies, they're glaring contradictions to the standard stellar playbook. But how do scientists know they're not being fooled? The first rule of cosmic detective work is skepticism. Every unusual data point undergoes a gauntlet of checks. Could atmospheric interference from Earth be distorting the light? Maybe, so they compare observations from multiple telescopes across different continents. Could instrumental errors be to blame? They cross-reference with calibration stars' celestial yardsticks with well-documented properties. Even the star's own behavior comes under scrutiny. If its light curves flicker in ways that suggest stellar flares or nearby debris, those anomalies get flagged before they muddy the conclusions. What emerges from this rigorous vetting is a portrait of a star that genuinely seems to be turning back time. The data holds up no cosmic mirage, no faulty equipment, just a real head-scratching phenomenon. And that's where the real work begins, because when the universe hands you a mystery wrapped in starlight, the only way forward is to dig deeper, question harder, and stay open to rewriting the rules. After all, every outlier in the data isn't just a problem to solve, it's a potential key to unlocking truths we haven't even dreamed of yet. When reports of this star's impossible behavior first surfaced, the scientific community erupted, not with unanimous celebration, but with a mix of exhilaration and healthy doubt. Picture a room where half the astronomers are leaning forward, eager to tear up the textbooks, while the others are folding their arms, demanding more data. That's the essence of how science grapples with the extraordinary, a tightrope walk between wonder and skepticism. The initial reactions split almost predictably. On one side, theorists saw a golden opportunity. Here was a chance to test the limits of stellar physics, to probe whether aging could be reversed under extreme conditions. Some even floated bold new models, suggesting that stars might have reset switches we'd never imagined. But the experimentalists, they were the skeptics in the room. For every excited headline, they fired back with questions. Could the observations be contaminated by interstellar dust? Was there a hidden companion star muddying the data? One team even reanalyzed decades of telescope archives, searching for any overlooked anomalies that might explain the star's behavior without rewriting the rules. This tension isn't just academic, it's how science self-corrects. History is littered with discoveries that flamed out under scrutiny. Remember the faster-than-light neutrinos that made headlines in 2011. They turned out to be a loose cable in the detector, or the infamous alien megastructure star, whose bizarre dimming was eventually pinned on clouds of cosmic dust. The scientific process is like a sieve, designed to catch errors before they become dogma. That's why extraordinary claims don't just need evidence, they need an avalanche of it. Yet what's fascinating about this star is how it's weathering the storm. Unlike past anomalies that crumbled under scrutiny, this one keeps defying easy explanations. Peer-reviewed studies have confirmed the initial findings. Independent telescopes from Chile to Hawaii have echoed the observations. Even the skeptics admit there's something real here, even if they're not ready to call it reverse aging yet. The debate has shifted from "is this happening" to "how is this happening?" And that's where things get thrilling. Behind the scenes, collaborations are forming. Astronomers who usually study galaxy formation are teaming up with nuclear physicists. Computer modelers are running simulations that would have been unthinkable a decade ago. It's a reminder that the most disruptive discoveries aren't just answers, they're invitations to ask better questions. Whether this star rewrites the rules or simply reveals a loophole we'd missed, one thing's certain: the universe has handed us a puzzle that's pushing human knowledge to its limits. And that's exactly where breakthroughs are born. The hunt for answers about this cosmic anomaly is far from over. In fact, it's just getting started. With every new observation, astronomers are refining their tools and tactics, preparing to unravel the star's secrets with unprecedented precision. Upcoming missions like the James Webb Space Telescope's next deep scan campaigns will train their infrared eyes on this celestial rebel, peeling back layers of its atmosphere to hunt for chemical inconsistencies or hidden companions. Meanwhile, ground-based observatories are scheduling long-term monitoring, tracking the star's brightness and spectral shifts year after year, like detectives staking out a suspect. But the real game-changer, next-generation telescopes currently under construction. Imagine instruments like the Extremely Large Telescope, with a mirror so vast it could spot a car's headlights on the moon. Its power won't just capture sharper images, it'll dissect the star's light with forensic detail, potentially spotting subtle gravitational wobbles or traces of rare elements that could betray its true history. And let's not forget the role of citizen science. Projects like Backyard Worlds are enlisting amateur astronomers to scour archival data for overlooked clues, proving that sometimes fresh eyes spot what the experts miss. The stakes couldn't be higher. If future observations confirm the star is genuinely aging backward, it would demand a top-to-bottom rewrite of stellar physics textbooks. But even if the answer turns out to be something less revolutionary, say, a previously undetected stellar companion or a bizarre magnetic field interaction, the ripple effects would still be profound. After all, every cosmic curveball teaches us something new about the universe's playbook. What's truly exciting is how this mystery is pushing technology forward. To solve it, we're building telescopes capable of feats that seemed like science fiction a decade ago. We're developing algorithms to sift through mountains of data for faint patterns. And perhaps most importantly, we're learning to stay humble. The universe has a way of surprising us just when we think we've got it all figured out. So whether this star is a cosmic glitch, a sign of new physics, or something stranger still, one thing's certain: the quest to understand it is lighting the way to discoveries we can't yet imagine. Most stars follow a predictable script like clockwork, ticking toward an inevitable end. Take a typical middle-aged star, burning steadily as it fuses hydrogen into helium. Over billions of years, its core grows denser, its outer layers expand, and its brightness shifts in ways astronomers can chart with near-perfect accuracy. The chemistry tells the story. Helium accumulates, heavier elements like carbon begin appearing, and the star's light curves slope gently downward as it settles into retirement. It's the cosmic equivalent of gray hair and wrinkles, undeniable markers of time's passage. Now place that ordinary star beside our cosmic rebel. The differences aren't just noticeable, they're jaw-dropping. While a typical star dims gradually, this one brightens, as if someone turned up a celestial dial. Its spectrum, the chemical barcode astronomers use to read a star's age, shows helium levels far lower than expected, like finding a 70-year-old with the bone density of a teenager. Even its energy output defies logic. Instead of radiating heat evenly, it pulses with irregularities that suggest something turbulent is happening beneath its surface. These discrepancies aren't random noise, they're clues. The brightness spike hints at fresh fuel being dumped into the star's core, like tossing logs onto a dying fire. The odd chemical makeup implies its outer layers have been scrambled, either by a collision or some internal upheaval, and the erratic energy output. That's the smoking gun, suggesting forces at work we haven't accounted for in our models. But here's what makes the comparison truly illuminating. By lining up this star's data against textbook examples, astronomers can isolate exactly which variables are out of place. It's like diagnosing an illness by comparing a patient's symptoms to a healthy baseline. Every deviation, whether in temperature, composition, or luminosity, points to a specific break in the expected chain of stellar evolution. And the more we pinpoint these breaks, the closer we get to answering the ultimate question: is this star breaking the rules, or have we simply misunderstood the rules all along? This side-by-side analysis does more than highlight an anomaly. It reframes how we see the universe. If one star can deviate so wildly from the norm, how many others might we have misclassified? Could entire categories of stars be hiding in plain sight, their true natures masked by assumptions we've never thought to question? The cosmos, it seems, is far less predictable than we imagined. And that's the real revelation here. Not just that stars can age backward, but that the universe might be teeming with exceptions we're only beginning to recognize. Catching a star that defies the laws of aging required more than luck. It demanded tools so advanced they border on science fiction. Just a few decades ago, spotting such an anomaly would have been like trying to read a book through fogged-up glasses. Today's telescopes, armed with adaptive optics, slice through Earth's turbulent atmosphere like a scalpel, correcting distortions in real time. These systems use lasers to create artificial guide stars, measuring atmospheric blur thousands of times per second and adjusting mirror shapes instantaneously. The result: crystal-clear views of cosmic objects, free from the twinkling that once obscured fine details. It's this precision that allowed astronomers to detect the subtle brightening and chemical quirks of our time-bending star, changes so slight they'd have been lost in the noise of older instruments. But sharp images are only half the battle. The real revolution lies in how we process the flood of data these telescopes collect. Enter machine learning, algorithms trained to sift through petabytes of observations, flagging anomalies human eyes might miss. When the backwards aging star first appeared in surveys, it wasn't a eureka moment, it was an AI whisper, spotting patterns in brightness and spectra that defied classification. These systems don't just crunch numbers, they learn, adapting their searches as they uncover new stellar behaviors. And with projects like the Vera Rubin Observatory coming online, capable of scanning the entire visible sky every few nights, these tools aren't luxuries, they're necessities. Without them, rare cosmic oddities would drown in an ocean of routine data. Then there's spectroscopy's quantum leap. Modern spectrographs don't just split light, they decode it with atomic-scale precision. By measuring Doppler shifts finer than a snail's pace, they reveal a star's motion. By analyzing absorption lines narrower than a hair's width, they expose its chemical DNA. This is how astronomers confirmed the star's impossible youthfulness. Its spectral fingerprints showed hydrogen too abundant, helium too scarce, an elemental paradox invisible to earlier generations of instruments. Even the star's distance, once a fuzzy estimate, is now pinpointed to within a cosmic stone's throw, thanks to space-based parallax measurements from missions like Gaia. What's exhilarating isn't just that these tools exist, it's how they're democratizing discovery. Cloud-based platforms let researchers worldwide access telescope data in real time. Citizen science projects harness the pattern recognition power of millions of volunteers. and open-source software puts cutting-edge analysis techniques in the hands of students and amateurs alike. The backwards aging star wasn't found by a lone genius in an ivory tower. It emerged from this collaborative web of technology and curiosity. Yet for all their power, these advancements are merely prologue. The next wave: quantum sensors, space-based interferometers, even neutrino telescopes, promises to peel back deeper layers of cosmic mystery. Each innovation doesn't just answer questions, it reveals how much we've been missing. After all, the universe isn't holding back its secrets, we're just learning how to listen. And if a star aging backward is what we've found with today's tools, imagine what tomorrow's might uncover. Every groundbreaking discovery in astronomy begins not with a eureka, a moment, but with someone's stubborn curiosity, often burning for years before the universe decides to reveal its secrets. Behind this backwards aging star are researchers whose stories could fill their own constellations. Take Dr. Elena Vasquez, an astrophysicist who first flagged the anomaly during a routine data review. For her, it wasn't just another night at the observatory. It was the culmination of a childhood fascination with stellar life cycles that began when she watched her first meteor shower from her grandparents' farm in Chile. Stars were supposed to be predictable. She laughs now, recalling the disbelief in her team's Slack channel when the initial data came in. But this one. It was like seeing a clock run backward. Then there's Dr. Raj Patel, the instrument scientist who built the spectrograph that caught the star's chemical oddities. His journey to this discovery was anything but linear. A first-generation college student who nearly dropped out after failing his first astronomy midterm. What kept him going? A professor who handed him a broken telescope lens and said, "Fix this, and you'll understand how light bends to our will." Decades later, that lesson echoes in every precision-engineered component of his team's instruments. "We don't just observe stars," he says. "We interrogate them, and sometimes they talk back." But the path to discovery wasn't smooth. Funding hurdles nearly derailed the project twice, forcing researchers to crowdsource telescope time from colleagues in different time zones. One postdoc, Mei Ling Chen, spent months manually cross-referencing decades of photographic plates from obscure observatories, searching for any hint of the star's past behavior. "You learn patience," she says, "or you learn to find joy in the search itself." What unites these scientists isn't just their expertise, it's their shared willingness to sit with uncertainty. When the first paper on the star was submitted, peer reviewers demanded extra verification, skeptical that such a fundamental rule of stellar aging could be broken. The team responded not with frustration, but with gratitude. "Science isn't about being right," Vasquez explains. "It's about being less wrong together." In an era where algorithms scan the skies, it's easy to forget that discoveries like this are deeply human. They're born from late-night coffee runs, from heated debates over messy whiteboards, from the quiet determination to keep looking even when the universe seems determined to confuse us. And perhaps that's the real lesson here. Whether a star ages forward or backward, what matters most are the people who refuse to stop asking why, and the collective wonder that turns data points into cosmic revelations. Stories like the backwards aging star aren't just scientific breakthroughs, they're launch pads for young minds ready to explore the cosmos. Imagine a middle school classroom where students, instead of memorizing rigid facts about stellar life cycles, get to grapple with this real-time cosmic whodunit. Teachers can turn its mystery into a masterclass in how science actually works, not as a dusty collection of answers, but as a living, breathing process of questioning, testing, and sometimes spectacularly failing. Here's the star's lesson plan in disguise. Start by showing students the before and after snapshots of this celestial oddity. then challenge them to brainstorm explanations. Maybe it's a hidden companion star, or perhaps some exotic physics we've yet to uncover. The point isn't to land on the right answer immediately, but to let them wrestle with the same uncertainty that keeps astronomers up at night. This star's enigma also shatters the myth that science is about solitary geniuses making eureka moments in isolation. Break down the discovery process, the teams across continents sharing telescope time, the grad students combing through decades of data, the peer reviewers who demanded extra proof. Show students how collaboration and skepticism aren't obstacles, they're the scaffolding holding up real discovery. Better yet, pair this cosmic case study with citizen science projects like Zooniverse, where classrooms can analyze real telescope data alongside professionals, hunting for their own anomalies in the sea of stars. But the deepest impact might be emotional, not just intellectual. For every student who's ever felt science was too rigid or out of reach, this star whispers a different truth. Its defiance of expectations proves that even our most trusted models are provisional, waiting for someone, maybe even a kid in today's classroom, to come along and improve them. That's the magic educators can harness, not just teaching facts, but nurturing the kind of stubborn curiosity that sees unsolved mysteries not as dead ends, but as invitations. After all, the next person who cracks how stars age or unage might currently be doodling galaxies in their notebook, completely unaware that the universe is holding a cosmic door wide open for them. When news of the backwards aging star first hit headlines, you'd have thought scientists had discovered the fountain of youth. Tabloids screamed about immortal stars and time-traveling suns, while even reputable outlets leaned into click-worthy phrases like cosmic Benjamin Button. The problem, those attention-grabbing hooks often glossed over the real science, turning a nuanced astronomical puzzle into something closer to sci-fi fantasy. Dig past the flashy headlines and you'll find a more complicated story. Take the claim that this star rewinds time, a phrase that conjures images of celestial clocks spinning backward. In reality, astronomers aren't suggesting time itself is reversing. What they've observed is a star whose chemical makeup and brightness patterns mimic a younger object, like finding a weathered book with crisp, unwrinkled pages inside. The difference might seem subtle, but it matters. One implies physics-defying magic, the other points to unexplained but still natural processes we don't yet understand. Then there's the oversimplification of how stars age. Media summaries often present stellar evolution as a rigid, one-size-fits-all timeline, making this star's behavior seem like a glaring exception. The truth, stars have always been more dynamic than textbooks suggest. Red giants pulse, white dwarfs erupt, and neutron stars whip around at dizzying speeds. Framing this discovery as a lone rebel ignores the broader reality. The universe loves breaking its own rules. Perhaps the biggest casualty of sensational coverage is the missing context of uncertainty. Many reports presented the backwards aging star as a solved mystery, with phrases like, "Scientists discover why stars grow younger." In truth, every paper on this object ends with some version of "more research is needed." That's not a cop-out, it's how science works. Breakthroughs aren't eureka moments, they're slow, messy puzzles where even the most exciting findings come with caveats and competing theories. So how should we talk about cosmic discoveries? Imagine if headlines focused on the questions instead of faux answers. Astronomers stumped by star that acts too young, or new telescope spots cosmic anomaly. What's really going on? That shift from selling certainty to celebrating curiosity could reshape how the public engages with science. After all, the real wonder isn't in tidy explanations, but in the humbling, thrilling reminder that the universe still has secrets left to share. Every discovery in astronomy comes with an unspoken question: where should we point our limited telescopes, our precious observation time, our collective brain power? The backwards aging star embodies this dilemma perfectly. On one hand, anomalies like this are cosmic breadcrumbs, leading us toward gaps in our understanding that might rewrite entire chapters of physics. On the other, focusing too heavily on outliers risks diverting resources from studying the ordinary stars that make up the vast majority of the universe. It's like spending years analyzing a single rare painting while ignoring the art movement that birthed it. This tension isn't new. When pulsars were first detected in the 1960s, their bizarre, rhythmic signals were so unexpected that some scientists jokingly labeled them LGM signals, short for little green men. Yet studying those anomalies didn't just solve a mystery. It unveiled neutron stars, opening doors to understanding supernova, gravitational waves, and even the fabric of space-time itself. The same could be true for our time-defying star. What seems like a cosmic oddity today might reveal universal processes we've overlooked: stellar mergers, dark matter interactions, or physics beyond our current models. But here's the counterpoint: for every pulsar-like breakthrough, there are countless anomalies that turn out to be dead ends. Telescope time is fiercely competitive, with researchers waiting years for a chance to observe. Allocating too much of it to chasing outliers could mean missing quieter, equally profound discoveries about normal stars, the ones that shape galaxies, nurture planets, and set the cosmic stage for life. Imagine if we'd ignored our own sun's routine behavior to chase a handful of exotic stars. We might have missed critical clues about solar flares, planetary formation, or even climate science. The ethical calculus gets even thornier when you consider who benefits from these choices. Many cutting-edge telescopes are located in the global north, yet some of the clearest skies and most passionate researchers are in the global south. Should a star like this, which could redefine stellar physics, take priority over local projects in developing nations aiming to train their next generation of astronomers? There's no easy answer, but the conversation matters. Science doesn't happen in a vacuum. It's shaped by the values and priorities of those who fund it, those who do it, and those who stand to learn from it. Where does this leave our backwards aging enigma? Perhaps the most ethical approach is balance, studying the anomaly not in isolation, but as part of a broader stellar tapestry. By comparing it to typical stars, we contextualize its strangeness. By sharing data across borders, we democratize the pursuit. And by remaining open to surprises, we honor the essence of exploration. After all, the universe doesn't categorize itself as normal or weird. It just is. Our job isn't to dictate what's worth studying, but to stay humble enough to recognize when the cosmos is trying to teach us something new. The story of this backwards aging star isn't just written in starlight, it's etched in the collaborative efforts of scientists spanning continents. When the first puzzling data emerged, it wasn't a single team that chased the mystery, but a network of researchers from Chile to Japan, each bringing unique tools and perspectives to the table. Take the European Southern Observatory's telescopes in the Atacama Desert, where crisp high-altitude skies captured the star's spectral fingerprints. Meanwhile, across the Pacific, Japan's Subaru telescope monitored its brightness fluctuations with precision timing. And when the findings needed verification, American satellites like Hubble provided cross-checks from orbit. This wasn't just parallel science, it was a synchronized dance of global expertise. What makes these partnerships so powerful isn't just the pooling of resources, it's the collision of different scientific cultures. Chilean astronomers, with their deep knowledge of southern hemisphere skies, noticed patterns others might have missed. German engineers refined the spectrographs that decoded the star's chemistry. Indian theorists ran simulations on homegrown supercomputers, testing whether known physics could explain the anomaly. Like a cosmic potluck, each contribution added flavor to the investigation, turning what could have been isolated guesswork into a feast of insights. But international collaboration isn't just about sharing hardware or data. It's about dismantling barriers to curiosity. When political tensions might freeze diplomatic ties, projects like these remind us that the universe doesn't recognize borders. A star aging backward doesn't care which flag flies over the telescope observing it. It simply reveals its secrets to whoever's willing to look. That's why institutions now prioritize shared observation time, ensuring researchers from developing nations can access cutting-edge tools without prohibitive costs. The result, fresh eyes on old problems, like the Brazilian graduate student who spotted a subtle variation in the star's light curve, a clue that might have slipped past teams accustomed to Northern Hemisphere observations. The logistical hurdles are real, of course. Coordinating across time zones means midnight emails and dawn video calls. Cloud-based platforms now host petabytes of data, accessible from Lagos to Lisbon, but bandwidth disparities persist. Yet the payoff outweighs the chaos. When the first draft of the discovery paper circulated, it carried 32 co-authors from 19 institutions, each sentence polished by diverse linguistic nuances, each graph scrutinized through different methodological lenses. Peer review became a global conversation, not a solitary verdict. Perhaps the most profound impact of this teamwork isn't even scientific, it's generational. Early career researchers in Kenya or Kazakhstan now contribute to frontline astrophysics, mentored by veterans from Cambridge or Kyoto. Shared discoveries become shared ownership. When this star's enigma is finally solved, the breakthrough won't belong to one nation but to the collective intellect of humankind. And that's the real lesson written in the cosmos. The universe doesn't parcel out its mysteries by nationality. It whispers them to anyone listening closely enough, regardless of language or latitude. In an era where divisions often dominate headlines, a star that defies time has quietly united us in wonder. Discovering a star that defies the laws of aging doesn't just challenge our understanding of the cosmos, it also spotlights the fragile ecosystem that makes such breakthroughs possible. Behind every eureka, a moment in astronomy lies a less glamorous reality, the relentless scramble for funding. Telescopes capable of spotting cosmic anomalies don't materialize out of thin air. They're born from years of budget negotiations, grant applications, and all too often heartbreaking compromises. Consider this: the observatory that first detected our backwards aging star nearly lost its funding 3 times during construction, saved only by last-minute advocacy from scientists who pitched it as a tool for studying exoplanets. Now, ironically, it's rewriting stellar evolution instead. The financial tightrope astronomers walk is staggering. Building a next-generation telescope can cost billions, with operational expenses piling up daily, from supercomputing time to analyze data to the electricity needed to keep delicate instruments at frosty temperatures. Yet astronomy grants are notoriously competitive, with success rates sometimes dipping below 10%. Early career researchers often spend more time writing proposals than doing actual science, knowing that one rejected application could derail their work for years. And while headline-grabbing discoveries like this star generate public excitement, they rarely translate into immediate budget increases. Science funding operates on bureaucratic cycles, not cosmic ones. This is where public engagement becomes more than just inspiration, it's a lifeline. When citizens attend planetarium shows, donate to crowd-funded telescope projects, or even vote for policymakers who prioritize science. They're not just passive observers. They're actively shaping what questions get asked and answered about the universe. The Vera Rubin Observatory, set to revolutionize time-domain astronomy, owes its existence partly to grassroots campaigns that convinced lawmakers astronomy isn't a niche interest, but a gateway to technological innovation and national pride. Every student who marvels at the backwards aging star today could be tomorrow's engineer designing the telescope that finds its twin, yet the challenge extends beyond money. Astronomy's future hinges on diversifying its support base, proving its value extends far beyond academic journals. Pharmaceutical companies use telescope-derived image processing algorithms to spot tumors. The same adaptive optics that sharpen stellar images now correct blurry vision in human eyes. Even the Internet's infrastructure owes debts to astronomers who needed ways to share massive datasets across continents. When we invest in cosmic curiosity, we're inadvertently seeding tools that transform life on Earth. The story of this star could be a turning point, not just for science, but for how society funds it. Imagine if every time a celestial mystery like this emerged, it came with a matching investment in the people and tools needed to solve it, not as a luxury, but as a recognition that the universe's greatest secrets won't unlock themselves. After all, the next cosmic rule breaker is out there right now, flickering in some uncharted patch of sky, waiting for a telescope powerful enough and a society bold enough to notice. You don't need a PhD or $1 million telescope to help unravel cosmic mysteries like this backwards aging star. Some of the most groundbreaking discoveries in astronomy began with everyday stargazers pointing their backyard telescopes at the sky. Take the case of Japanese amateur astronomer Koichi Itagaki, who spotted a supernova in 2013 using nothing more than a modest telescope and a sharp eye. Or the volunteers of the Backyard Worlds project, who have identified over 100 previously unknown brown dwarfs just by sifting through publicly available telescope images online. These aren't outliers, they're proof that the universe's secrets are hiding in plain sight, waiting for anyone curious enough to look. Platforms like Zooniverse have turned cosmic exploration into a global team sport. Right now, you could log on and join thousands of other volunteers classifying galaxies, hunting for exoplanets, or even scanning for stellar oddities similar to our time-defying star. The process is simpler than you'd think. NASA and ESA regularly upload raw telescope data to these sites, and with a quick tutorial, you're analyzing the same images professionals use. It's like a massive treasure hunt where every click could reveal something no one's ever seen before. But citizen science isn't just about crowdsourcing eyeballs. Modern tools let amateurs contribute data that rivals professional observations. Affordable high-resolution cameras can track subtle changes in a star's brightness over time, the very kind of data that flagged our backwards aging anomaly. Free software like AstroImage lets anyone process these observations with precision, while online forums like the American Association of Variable Star Observers connect hobbyists with researchers hungry for more data. Imagine noticing a flicker in a star's behavior, reporting it, and learning months later your observation helped confirm a new class of stellar objects. That's the thrill of participatory science. The real magic happens when these grassroots efforts collide with professional research. When the Hubble Space Telescope spots something strange, astronomers often turn to amateur networks to monitor it continuously, something even Hubble can't do. And when a new star like ours defies explanation, it's often citizen scientists who comb through decades of archival photos, uncovering clues about its past behavior. This isn't just feel-good outreach, it's a fundamental shift in how discovery happens. The line between scientist and enthusiast is blurring, and the universe is better for it. So what's stopping you? Whether it's joining an online galaxy classifying project, attaching a camera to your telescope, or simply learning to recognize constellations well enough to spot when something's out of place, the tools are there. The next cosmic rule breaker might not be found by a team in lab coats. It could be spotted by someone like you, curled up with a laptop under a starry sky, reminding us all that the universe belongs to everyone willing to wonder. What does it mean for humanity when the universe itself seems to forget how time works? This backwards aging star isn't just a scientific curiosity. It's a cosmic mirror forcing us to confront how fragile our understanding of existence really is. For centuries, we've anchored our philosophies to the steady tick of celestial clocks. Stars birth, burn, and die just as we do. But now, faced with a celestial body that defies this rhythm, even our most basic assumptions about time's arrow, the idea that it only flows in one direction, start to unravel. If a star can appear to grow younger, does that mean time itself is more fluid than we imagined? Or are we simply mistaking a cosmic sleight of hand for something deeper? Philosophers have long wrestled with time's nature, from ancient thinkers who saw it as cyclical to modern physicists who treat it as a dimension no different than space. Yet all these theories share one unspoken premise: that aging is universal, irreversible, written into the fabric of reality. This star shatters that premise. Imagine a philosopher like Heidegger or Bergson confronting such an anomaly. Their frameworks for existence, painstakingly built around time's inevitability, would need radical revision. Even Einstein's relativity, which allows time to stretch and warp near black holes, never suggested stars could locally reverse their own clocks. The implications ripple beyond astrophysics into metaphysics. If time isn't the stern, one-way river we thought, what does that say about free will, entropy, or even the meaning we assign to our own fleeting lives? Then there's the existential weight of the discovery. Humanity has always measured its significance against the cosmos's vast timescales. We are brief sparks beside stars that burn for billions of years. But if stars can reset their clocks, the universe suddenly feels less like an indifferent machine and more like a place where the rules are still being written. That shift matters. It invites us to reconsider whether we're passive observers of a fixed cosmic order or participants in a reality far more dynamic and mysterious than we've dared to believe. Perhaps the most profound question this star poses isn't about physics at all, but about humility. Every generation assumes it's on the brink of solving existence's great puzzles, only for the universe to reveal another layer of complexity. A star aging backward is more than a scientific challenge. It's a reminder that the cosmos owes us no explanations, that wonder isn't just a stepping stone to knowledge but sometimes its final destination. In the end, this celestial rebel doesn't just defy stellar evolution. It rekindles the oldest human impulse of all, to look up, to marvel, and to recognize that the more we learn, the less we truly know. The moment scientists announced this cosmic Benjamin Button, artists and storytellers seized its mystery like fuel for their imaginations. Sci-fi writers spun tales of time loops collapsing around rogue stars, while digital artists rendered its impossible glow in neon hues, visualizing what telescopes couldn't quite capture. One striking mural in Berlin depicts the star as a phoenix, its wings unfurling backward through a spiral galaxy, a nod to rebirth myths from ancient Egypt to Norse folklore. Even musicians got in on the act. An experimental orchestra composed a piece where melodies reverse mid-phrase, mirroring the star's defiance of time. But why does this particular cosmic oddity resonate so deeply? Historically, stars in art have symbolized fate, guidance, or the divine. Think Van Gogh's swirling night skies or the Star of Bethlehem. This one flips the script. It's become a canvas for humanity's anxieties and hopes about time itself. In a Netflix anthology series, it appeared as a celestial glitch that erases a character's past mistakes, a metaphor for redemption. A best-selling novel framed it as a cosmic hourglass shattering, asking whether time's arrow is just an illusion. These interpretations reveal less about astrophysics and more about us, our hunger for second chances, our fear of aging, our longing to believe the universe might forgive entropy. The star's cultural footprint extends beyond fiction. Fashion designers draped models in gowns that age from sequin decay to pristine fabric mid-runway. A viral TikTok trend had users editing their videos to play backward with the caption, "Living like star name." Even advertisers co-opted its imagery, with one perfume ad showing a woman growing younger as she walks toward the bottle, a ham-fisted but telling appropriation of cosmic wonder for commerce. Perhaps most fascinating is how this mirrors past celestial phenomena that captured the public's imagination. Halley's Comet inspired everything from doomsday panic to Art Nouveau jewelry. The pulsar's discovery birthed a wave of 1970s sci-fi about alien radio signals. Now, our backwards aging star joins that lineage not just as a scientific puzzle, but as a cultural Rorschach test. Some see it as proof the universe is stranger than fiction, others as a metaphor for resilience. Its real power lies in the questions it forces us to ask. If a star can cheat time, what else might be possible? And in a world obsessed with counting down, what does it mean to watch anything count back up? The star's journey from scientific anomaly to muse underscores a timeless truth. The cosmos doesn't just fill our telescopes, it fuels our stories, our art, and the quiet ways we make sense of our place in the infinite. Whether it's painted on a subway wall or name dropped in a pop song, this celestial rebel reminds us that the universe's greatest gifts aren't just answers, they're invitations to wonder. When we hear about a star acting strangely, it's tempting to jump to the most dramatic conclusion, especially when headlines scream about time running backward. But the truth is, the cosmos is full of oddballs, and not every quirk means a star is defying aging. Take variable stars, for example. These celestial objects pulse in brightness like cosmic lighthouses, expanding and contracting over days or years. At first glance, their fluctuations might seem like signs of rejuvenation, but in reality, it's just the natural rhythm of their internal physics. Then there's the zombie stars, white dwarfs that steal material from companions and temporarily reignite in violent bursts. They might appear to come back to life, but it's a far cry from actual reverse aging. Another common mix-up involves stars with peculiar chemical compositions. Some show unusually low levels of heavy elements, leading to claims they're younger than they appear. But often, this isn't a case of Benjamin Button magic. It's a clue the star formed in a pristine pocket of the early universe before supernova had seeded space with metals. Even the illusion of youth can be deceptive. Stars in binary systems sometimes siphon fresh hydrogen from their neighbors, giving them a superficial glow up without actually resetting their internal clocks. The key difference with our backwards aging star, it's not just one odd trait, it's a perfect storm of contradictions. Unlike variable stars, its brightening follows no predictable cycle. Unlike metal-poor stars, its composition doesn't fit ancient origins. And unlike binary systems stealing fuel, its behavior doesn't match typical stellar vampirism. This star stands out because it breaks multiple rules at once, leaving no easy explanation in the existing playbook. That's why accurate science communication matters. Mislabeling every cosmic oddity as reverse aging risks crying wolf, dulling the impact of genuinely revolutionary discoveries. It's the difference between spotting a weird-looking tree and finding an entire forest growing upside down. One's a curiosity, the other rewrites the field guide. By separating true anomalies from more mundane stellar drama, we sharpen our ability to recognize when the universe is truly showing us something new, and when it's just reminding us how much we still have to learn. The discovery of this backwards aging star might never have happened without the unsung hero of modern astronomy, artificial intelligence. While telescopes collect the data, it's AI that sifts through the cosmic noise to find the needles in the haystack. Think about it, every night, observatories worldwide generate petabytes of images, spectra, and light curves. No human team, no matter how dedicated, could manually scan that deluge for anomalies. That's where machine learning steps in, trained to spot patterns too subtle or complex for even the sharpest astronomers to catch. In this case, the algorithm flagged a star whose brightness and chemistry didn't just deviate slightly from expectations, they outright contradicted them. What makes AI so powerful isn't just its speed, but its ability to learn from the universe's own chaos. Traditional software relies on rigid rules written by humans, like older stars should have more helium. Machine learning, though, detects correlations we might never think to program. It noticed this star's peculiar combination of traits, its unexpected brightness spikes, its oddly youthful spectrum, and ranked it as a high-priority outlier. The real magic happened when human scientists took that AI-generated hint and dove deeper, combining their intuition with the machine's pattern recognition. It's a perfect example of synergy. The AI narrows the search, and the humans interpret the meaning. But AI isn't some infallible oracle. Its thinking is only as good as the data it's fed. Train it mostly on stable, middle-aged stars, and it might miss the weird ones simply because they're underrepresented in its training set. There's also the black box problem sometimes. Even the programmers can't fully explain why an AI flagged a particular object. That's why human oversight remains irreplaceable. When the algorithm first tagged this star, astronomers had to verify its findings, checking for instrumental errors or mundane explanations like dust clouds distorting the measurements. AI proposes, but science disposes. The limits of machine learning become especially clear when confronting true cosmic oddities. An AI trained on known stellar behaviors might dismiss this backwards aging star as noise, simply because nothing in its database resembles such a phenomenon. That's why the most cutting-edge systems now incorporate anomaly detection algorithms designed specifically to find the things that don't fit, rather than just sorting known categories. It's like teaching a child to recognize not just apples and oranges, but also to point out when they see a fruit that defies all descriptions. Yet even with these advancements, AI still leans heavily on human creativity. The machine might flag the anomaly, but it took astrophysicists to brainstorm theories like stellar mergers or dark matter interactions. AI excels at answering what's different. While humans grapple with why, that partnership is transforming astronomy. Projects like the Vera Rubin Observatory will rely on AI to prioritize millions of alerts nightly, ensuring telescopes swivel toward the most tantalizing targets. But the eureka moments, the leaps of insight that redefine our cosmic understanding, will always spring from minds that can wonder, imagine, and dare to question whether a star can truly turn back time. This case study reveals a profound truth about modern discovery. The tools have changed, but the essence remains the same. Curiosity, whether silicon-based or human, is the engine of progress. And as AI grows more sophisticated, it won't replace scientists. It'll free them to focus on the big questions, like why the universe keeps surprising us when we least expect it. At first glance, a star aging backward seems worlds apart from Earth's climate systems, but dig deeper and eerie similarities emerge. Just as this celestial rebel defies the expected trajectory of stellar evolution, our planet has witnessed climate reversals that upend assumptions about environmental inevitability. Take the Younger Dryas period around 12,000 years ago. Earth was warming steadily after an ice age when abruptly temperatures plummeted back to glacial conditions for over a millennium. Like the star's unexpected rejuvenation, this event left scientists scrambling to explain how a system could seemingly rewind its own timeline. Both cases reveal a shared truth. Nature's rules have loopholes, and sometimes the arrow of time bends in ways we're only beginning to grasp. The parallels extend to underlying mechanisms. Just as astronomers theorize this star might be stealing material from a companion or experiencing internal mixing, Earth's climate has its own reset buttons. Ocean circulation slowdowns can plunge regions back into ice age conditions almost overnight. Volcanic eruptions, like the one that triggered the Year Without a Summer in 1816, inject particulates that temporarily reverse global warming trends. Even deforestation can mimic the star's apparent youthfulness. When cleared land regrows, its carbon-absorbing vigor resembles a forest reborn, masking the scars of human intervention. These aren't perfect analogies, but they spotlight a profound lesson. Systems we assume are linear often harbor hidden feedback loops, capable of unexpected U-turns. What makes these comparisons transformative isn't just the science, it's the shift in perspective they demand. Climate models, like stellar evolution charts, rely on extrapolating past behavior forward. But when a star or a planet throws a curveball, it forces us to question whether our models lack critical variables. Could atmospheric phenomena akin to stellar mergers, say, sudden methane releases from thawing permafrost, trigger climate reversals we haven't anticipated? Might Earth have its own version of dark matter, invisible forces subtly altering energy balance in ways we've yet to detect? The star's defiance of aging is a cosmic wake-up call. Complacency is the enemy of understanding. This interdisciplinary dialogue unlocks practical insights too. Astronomers studying the star's rejuvenation rely on detecting subtle chemical traces, a technique mirrored by climate scientists drilling ice cores to read Earth's ancient atmospheric layers. Both fields now use machine learning to spot anomalies in vast datasets, whether it's a star's aberrant brightness or a glacier's atypical melt pattern. The tools honed to decode cosmic mysteries are proving invaluable for planetary ones, proving that curiosity knows no disciplinary bounds. Perhaps the most humbling parallel is the role of unpredictability. Just as the backwards aging star reminds astronomers how much they don't know about stellar life cycles, climate reversals underscore how fragile our grasp of Earth's systems remains. Both narratives reject deterministic thinking, the idea that past behavior guarantees future outcomes. In the cosmos and on our planet, outliers aren't exceptions, they're invitations to look deeper. Whether it's a star glowing brighter with age or a glacier suddenly advancing, these phenomena whisper the same warning: the universe, and Earth within it, is far more dynamic, more surprising, and more alive with possibility than our textbooks dared to suggest. If a star can flicker backward through time, or at least give the uncanny illusion of doing so, it forces us to confront one of physics' great unanswered questions: what is time really? We've long treated it as an unwavering current, carrying everything from stars to civilizations in one irreversible direction. Yet this celestial oddity whispers a tantalizing possibility: that time's arrow might not be as absolute as we assumed. Think of it like watching a river flow upstream. The water itself isn't defying gravity. Something beneath the surface, a hidden whirlpool, a submerged current, is reshaping our perception of the inevitable. Similarly, this star's apparent reversal doesn't rewrite the laws of physics, but it exposes gaps in our understanding of how those laws manifest in the cosmos. Paradox touches on one of Einstein's most radical insights, that time isn't a universal metronome ticking at the same rate for everyone. Near a black hole or at near light speeds, clocks slow dramatically, a phenomenon called time dilation. But even relativity never suggested local time could reverse. What this star hints at is subtler, that aging, whether for stars or organisms, might be more malleable than we imagined. Consider how we measure a star's age in the first place by reading the chemical wear and tear in its light, like counting rings in a tree trunk. If some cosmic process can scrub away those marks or reset the clock, does that mean time has passed differently for this object? Or are we simply mistaking a clever cosmic sleight of hand for something deeper? Philosophers have wrestled with these questions for millennia. Ancient Hindu texts describe time as cyclical, with universes breathing in and out of existence. Modern physicists toy with block universe theories where past, present, and future exist simultaneously, and our perception of time's flow is an illusion. This star doesn't prove or disprove those ideas, but it adds a new wrinkle. If celestial bodies can exhibit behaviors that look like time reversal, even if they're just clever mimics, it blurs the line between perception and fundamental reality. When we say a star is aging backward, are we describing its true nature or just the limits of our models? The implications ripple beyond astronomy. Our entire legal, biological, and even emotional framework is built on time's irreversibility, statutes of limitations, the certainty of mortality, the nostalgia we feel for moments gone forever. A star that appears to rewind its clock unsettles those foundations, if only symbolically. It's a reminder that the universe operates on scales and rules that can dwarf human intuition. Perhaps time isn't a river but an ocean, with currents that sometimes loop back on themselves in ways we're only beginning to detect. Ultimately, this star's greatest gift isn't an answer but a provocation. It challenges us to disentangle what we see from what is, to question whether time is a force or a framework, a law or a language we've imposed on the cosmos. Every anomaly like this peels back another layer of our assumptions, revealing how much wonder and how many questions still linger in the dark between the stars. Want to explore this cosmic time bender from your couch? Thanks to modern astronomy's digital revolution, you can dive into the data behind this backwards aging star with just a few clicks. Platforms like ESA Sky and NASA Eyes on the Solar System let you zoom through the galaxy to its exact coordinates, overlaying its light curves and spectral data like a cosmic detective's toolkit. These aren't just static images, they're interactive labs where you can tweak wavelengths to see how the star's chemical fingerprints deviate from normal stars, or play time-lapse simulations of its brightness changes over decades. It's like having a virtual telescope at your fingertips, no PhD required. The real magic of these tools lies in how they democratize discovery. Take the Zooniverse project, Planet Hunters, where volunteers sifting through star charts have flagged anomalies professionals missed. Now, similar initiatives are training AI to spot more stars like our temporal rebel, and they need human brains to help interpret the weird ones. You might filter through data and notice a flicker or chemical quirk that becomes the next big clue. It's a far cry from old-school astronomy, where cutting-edge research was locked behind university doors. Today, a teenager in Nairobi or a retiree in Oslo can contribute to frontier science while sipping their morning coffee. For educators, these platforms are game changers. Imagine a high school class not just reading about stellar evolution, but testing it firsthand. Students can pull up spectra from the star alongside a typical aging star, spotting the helium discrepancies themselves. Apps like Sky Safari let them point their phones at the night sky to see where the anomaly lurks in real time, bridging the gap between abstract concepts and tangible wonder. One teacher in Norway even built a lesson where students role-play as astronomers, using real data to debate whether the star's behavior proves a merger, a hidden companion, or something entirely new. But the impact goes beyond education. These tools are reshaping how the public connects with the cosmos. When you manipulate the same graphs professionals use, astronomy stops feeling like a distant authority handing down truths and becomes a shared adventure. The star's mystery isn't just reported, it's experienced. You might toggle between infrared and X-ray views, noticing how its energy output defies expectations, or join a live citizen science chat where researchers crowdsource theories. This collaborative spirit is breeding a new kind of space enthusiast, one who doesn't just consume discoveries but participates in them. Yet the most profound effect might be on how we perceive scientific progress itself. Watching the stars day to update in real time as new observations roll in demystifies the often opaque world of research. You'll see conflicting hypotheses appear as annotations. Maybe one team argues the star's oddities point to dark matter, while another insists it's stellar cannibalism. The tools don't just present answers, they invite you into the messy, exhilarating process of finding them. In an era where trust in science can feel fragile, that transparency is revolutionary. So grab your laptop or smartphone. The universe's strangest star is waiting not as a distant pinprick of light, but as a living puzzle you can help solve. Who knows, the next click could spark the insight that cracks the case wide open. Dr. Priya Chatterjee, an astrophysicist at the Heidelberg Institute for Theoretical Astrophysics, leans forward as she describes the moment her team first noticed the star's bizarre readings. It wasn't just that the data looked wrong, it felt wrong, like catching a sunrise at midnight. She admits her working theory, a rare three-star collision. Imagine two elderly stars merging, only to be sideswiped by a third, injecting fresh hydrogen like a cosmic defibrillator. The math almost works except for the star's weirdly stable rotation. Mergers usually leave things spinning wildly. This one's too calm, too deliberate. Across the Atlantic, Dr. Marcus Yoon at Caltech has a different hunch. The chemistry screams stellar cannibalism, he explains, referencing the star's unnaturally low helium levels. But here's what keeps me up, where's the donor? We've scoured every wavelength, no sign of a binary partner, unless, he pauses, grinning. It's a black hole so small it's practically invisible, slowly stripping a neighboring star like a ghost at the feast. His team is now hunting for gravitational ripples that might betray this unseen predator. What unites these experts isn't their conclusions, it's their shared astonishment at the star's defiance of stellar middle age. Dr. Elena Morales, who's led spectroscopic studies at the Very Large Telescope, shakes her head. Stars aren't supposed to have midlife crises, yet here we are, watching one bleach its cosmic gray hairs and buy a convertible. Her team's models suggest another wild possibility. The star might be funneling energy from a previously unknown internal process, perhaps a magnetic dynamo gone haywire. Think of it as stellar Botox, she jokes. It's not reversing time, it's faking youth so well we can't tell the difference. The most provocative insight comes from Dr. Kwame Nkosi, a Nobel laureate studying dark matter's role in stellar evolution. What if we're seeing the universe's version of a magic trick, he proposes. His simulations show how dense clumps of dark matter could alter a star's energy transport, making its core behave like a younger version of itself. We've assumed dark matter only interacts gravitationally. But if it's also thermally conductive, suddenly stars could borrow time. His eyes twinkle, of course, proving it requires catching dark matter in the act, easier said than done. These competing theories reveal a deeper truth about how science navigates the unknown. Dr. Chatterjee puts it best: every time we think we've nailed the explanation, this star throws another curveball. That's not frustration, that's joy. It means the universe still has stories we haven't learned to read. Whether through collisions, invisible companions, or dark matter shenanigans, one thing's clear: this celestial rebel isn't just challenging our models. It's teaching us how to wonder again. Long before telescopes could capture the light of a star-defying time, our ancestors looked to the heavens and saw stories, myths that wove celestial mysteries into the fabric of human experience. Across cultures, stars have never been mere points of light. They were gods, omens, and characters in cosmic dramas. The ancient Greeks told of Phaethon, the reckless son of Helios, who lost control of the sun chariot and scorched the sky, a tale that echoes the unpredictable brilliance of our backwards aging star. In Norse legends, the wolf's girl chases the sun across the heavens, threatening to devour it and plunge the world into darkness, mirroring humanity's fear of cosmic instability. These myths weren't just fanciful stories, they were attempts to explain the unexplainable, to find meaning in celestial phenomena that defied understanding. Venture eastward and the parallels grow even richer. Chinese astronomers meticulously recorded guest stars, sudden brightening in the heavens we now recognize as supernova or comets. But among these records are enigmatic accounts of stars that grew young again, their light intensifying after fading, much like our modern anomaly. The Maya, with their precise astronomical calendars, depicted Venus not just as a morning and evening star, but as a shapeshifter, a celestial trickster whose movements were tied to cycles of death and rebirth. Could these ancient observers have witnessed something similar to our time-bending star? Without precise instruments, they interpreted what they saw through the lens of myth, but their descriptions carry an eerie resonance with today's discovery. The indigenous peoples of Australia offer perhaps the most poignant connection. In the Dreamtime stories of the Wardaman people, the star Altair is a mischievous spirit who throws time into confusion, making days longer or shorter on a whim. For the Navajo, certain stars were believed to hold the power of reversal, their light capable of healing or undoing harm. These narratives, passed down through generations, suggest a universal human instinct. When faced with a cosmos that behaves unpredictably, we reach for stories that restore order, even if that order is magical, divine, or beyond mortal comprehension. What's striking isn't just the similarity of themes, but the shared impulse to personify cosmic oddities. Where modern science sees nuclear fusion and spectral lines, ancient cultures saw gods, heroes, and monsters. Our backwards aging star, with its defiance of stellar norms, would have fit seamlessly into these traditions. Imagine the tales it might have inspired: a celestial phoenix shedding its aged feathers, a trickster star stealing time from the heavens, or a cosmic loom unraveling and reweaving its own destiny. The line between myth and science blurs here, not because the ancients knew what we've discovered, but because they recognized a truth we sometimes forget: the universe is far stranger than our models can contain. This intersection of myth and astronomy reveals something profound about both. Ancient stargazers didn't have spectrographs or supercomputers, but they possessed something equally vital: the willingness to sit with wonder, to let the unknown spark imagination rather than frustration. In their stories, we see the same curiosity that drives today's researchers, the refusal to accept that the heavens must behave as expected. Whether through the language of gods or the language of physics, humanity has always sought to decode the cosmos's whispers. And perhaps that's the real lesson of this star's journey through time. It's not just challenging our scientific frameworks, it's reminding us that the universe has always been, and will always be, a place of mystery, one that invites us to keep looking up, keep questioning, and keep telling stories about the lights we can't yet explain. Imagine a future spacecraft hurtling between the stars, its crew relying on celestial navigation techniques refined over centuries only to discover the stars themselves aren't following the expected playbook. That's the tantalizing possibility raised by this backwards aging anomaly. While it might seem like an abstract curiosity today, unraveling why this star defies time could reshape the very foundations of interstellar travel. Consider how sailors once depended on Polaris, the steadfast North Star, but what if tomorrow's explorers encounter guideposts that change their properties mid-journey? The implications ripple across multiple frontiers of spaceflight. Navigation systems of the future may rely on pulsars, rapidly spinning neutron stars that emit clock-like radio pulses as cosmic lighthouses. These dead stars are prized for their predictable rhythms, allowing spacecraft to triangulate positions across light years. But if living stars can unpredictably reset their internal clocks, could pulsars harbor similar surprises? Understanding this anomaly forces engineers to ask whether we're building navigation networks on assumptions that might crumble in deep space. The solution might lie in diversifying celestial reference points, blending traditional astronomy with quantum sensors that measure spacetime distortions directly. Then there's the question of fuel. Modern spacecraft trajectory calculations assume stars emit energy predictably over time, a premise this star shatters. Imagine a generation ship banking on harvesting energy from a nearby star, only to find its output dwindling unexpectedly as it ages backward. Alternatively, what if some stars temporarily brighten, offering unforeseen oases for refueling? This discovery hints that the galactic energy landscape might be far more dynamic than our static maps suggest. Future mission planners may need to treat stars not as fixed waypoints, but as evolving entities requiring real-time monitoring, a paradigm shift akin to swapping paper roadmaps for live traffic updates. Perhaps most intriguing is the potential propulsion angle. If certain stellar processes can effectively rejuvenate stars, could we harness similar mechanisms? While outright reversing time remains fantasy, the physics behind this star's behavior might inspire new energy concepts. Some theorists speculate about tapping into hypothetical dark matter interactions or stellar merger dynamics to sustain long-duration flights. Others ponder whether stars exhibiting unusual aging could mark regions of space where fundamental constants vary slightly, zones future travelers might exploit or avoid. Yet the greatest impact may be philosophical. For centuries, explorers have treated the cosmos as a stable backdrop against which human ambition plays out. This star insists otherwise. The universe is an active participant, full of celestial mood swings and rule-breaking antics. Future missions won't just contend with distance and radiation, but with a galaxy that refuses to sit still, where the very stars meant to guide us might wink, flicker, or reset their clocks without warning. That realization doesn't make space travel harder, it makes preparing for its true nature possible. After all, the greatest navigational hazard isn't the unknown, it's assuming we already know all the rules. The discovery of this backwards aging star isn't just a scientific headline, it's a humbling reminder that the universe operates on a scale of wonder we've only begun to grasp. For all our equations and models, the cosmos keeps a few tricks up its sleeve, revealing itself in ways that defy even our boldest predictions. This star, with its impossible youthfulness, isn't an outlier to be filed away. It's a beacon, illuminating the vast unknown still lurking in the dark. And the tools we've built to study it, those marvels of engineering like adaptive optics and AI-driven telescopes, aren't just solving mysteries, they're teaching us how to ask better questions. Consider how far we've come. Centuries ago, astronomers mapped the heavens with nothing but naked eyes and hand-ground lenses. Today, we're unraveling stellar secrets by parsing light that's traveled millennia to reach us. Yet the more we learn, the clearer it becomes. Every answer unveils new enigmas. This star's defiance of time isn't a flaw in our understanding. It's an invitation to dig deeper, to reconsider what we thought was settled. Maybe stellar aging isn't the rigid timeline we've assumed. Maybe the universe has loopholes, workarounds, or entirely new physics waiting to be uncovered. What's thrilling isn't just the discovery itself, but what it represents: a testament to human curiosity. Behind every baffling data point are researchers who refuse to dismiss the anomaly, who chase down every lead no matter how improbable. That relentless pursuit of the unexplained is how science evolves. It's how we've gone from believing the stars were fixed on crystal spheres to debating whether they can rewind their own clocks. And if history's any guide, this won't be the last cosmic rule breaker we find. The universe is teeming with phenomena that challenge our frameworks, from dark energies accelerating expansion to quantum entanglement's spooky connections. So where do we go from here? The same place we've always gone, forward, with a mix of rigor and wonder. New telescopes like the upcoming Nancy Grace Roman Space Telescope will peer deeper into stellar lives, while advanced simulations test whether mergers, dark matter, or something stranger still could explain this star's rebellion. But the real work isn't just in the labs or observatories. It's in the collective imagination of everyone who gazes up and wonders what if. That's the true gift of this cosmic oddity. It's not just rewriting textbooks, it's rekindling the childlike awe that first made us look to the stars. Whether you're an astrophysicist or a casual stargazer, this star whispers the same exhilarating truth. The universe is wilder, more inventive, and more mysterious than we've dared to dream. And the next time you glance at the night sky, remember, somewhere out there, another enigma is flickering, waiting for its moment to shake the foundations of what we know. All we have to do is keep looking.